Assalamu alaikum. It's me, Hammad Shaukat. We are starting new course, Principal Method Applications of Nuclear Tracks. This is our new course, new series of this Principal Methods Applications of Nuclear Tracks. Stay tuned with us. Maybe it's about 33 lectures of total, and today is our first lecture. And today we will discuss about radiation interactions. We will follow Galen Canal book, third edition. Okay, so the first today we will discuss about radiation interactions. There are three types of radiation interactions. First one is heavy charge particles. What does this heavy charge particle means? Heavy charge particles means, like you can say, heavy like proton. Electron is not an heavy charge particle. uh, Above than proton, alpha particle having two protons, so it's a you can say heavy charge particle. The second one is fast electrons. Okay, the fast electrons, what is the fast electrons? Fast having a speed high, so definitely it has mass less. Okay, mass less mass, you can say. Okay, and the third thing is basically uncharged particles, uncharged radiations, you can also say. You can know that uncharged particles are either, you will know that neutrons, or you can say neutrons, are chargeless particles. Okay, but they are in the regime of heavy charge particles. Okay, heavy uncharged particle, you can say. Okay, and similarly, that alpha rays and gamma rays are also for the uncharged radiations. Okay, but these are for the case of fast electrons. So this is all about, and first of all we will discuss about heavy charge particles. So the heavy charge particle is basically the maximum energy that can be transferred from a charged particle. Let's suppose a charged particle is coming, and that charged particle some mass m, having some kinetic energy E, having to interacts with some atoms, with some material, with an electron rest mass m naught. Okay, in a single collision, the amount of energy loss in the collision of when a particle having an energy E, having del kinetic energy E, when it interacts with the matter, the amount of energy uh, release, you can say the empirical formula is basically this: 4e m naught divided by m. Okay, m is basically the mass of the material where the particle interacts, and m naught is the rest mass of an electron. E is the amount of energy that transferred from charged particle to that material. Okay, so this is empirical formula, and you can also say that it's 1 by 500 particles energy per nucleon. And in this case, as the energy decreases when the particle collide with some material, energy decrease in that material, and it's the velocity of that charge particle is decreases by 1 by v square. Okay, 1 by v square. Okay, you know that when charged particle interact with matter, so as I already told you, energy decreases, and its also velocity also decreases by a factor of 1 by v square. Okay, so the next concept I have to draw you. First of all, let me explain you something more. The thing is, the radiation in the right column are uncharged because X-rays and gamma rays having no charge, they are chargeless, but they are in the regime of fast electrons. Okay, and instead these radiations must undergo catastrophic interaction. Okay, similarly you can say that, let me explain you furthermore. Interaction of high charge particles in the regime of there are only two conditions. depending on the proximity of the encounter, the impulse may be sufficient either to raise the electron when you know that the charge particle is coming, either when it impulse encounter, this impulse may be sufficient either to increase the electron, you can say, to the higher lying shell, or you can say this is excitation, or another thing is to remove completely an electron, which you can say from the atom, also known as ionization. So these two concepts may be happen when a charged particle is interacting with some material. Okay, so these are some important thing which I told you, and the thing which I told you also, the maximum energy that can be transferred from charged particle to of if a charged particle has mass m and having kinetic energy e to an electron having rest mass m naught in a single collision, it has a energy loss of 4 e m naught divided by m. These are some important things we have to know how, and we also the important thing I have to go through to you is the product of these encounters in the observer are either excited or ion pairs, because there are only two possibilities, either the atom electron excite or either the electron ionize. So if it's excited, so it is excited atom, and if it is ionized, so it becomes ion pairs. Okay, so each ion pair is made up of free electrons and the corresponding positive ion of an observer atom from which an electron has been totally removed. Okay, so these are some important things we have to discuss, and furthermore we will discuss our next thing, which is the stopping potential. What is basically the stopping potential in simple words? I can say that the linear, you can say it's a linear, the linear stopping potential, it is denoted by, let me explain you that, stopping potential, it is denoted by symbol capital S. Okay, stopping potential. And what is stopping potential? Basically the linear stopping potential you can simply define as for charge particle in a given observer is simply defined as, you can say, the differential energy loss. Okay, you can say the differential energy loss, you can say differential energy lost, energy is lost for particle. Okay, when particle interact with some material, and divided by the differential path length. Okay, dx as the energy loss, so it is a minus sign here, so your stopping potential becomes equals to the amount of energy loss for that particle within the material divided by the corresponding differential path length. Okay, so this is also called as a simple, you can say it's specific as, okay, specific energy loss. You can say this is specific energy loss, or you can say stopping potential, and another name it as, you can say, rate of energy loss. Okay, the rate of energy loss, rate of energy loss when a particle interacts some matter and lost some energy inside. Okay, so this is all about, and this is the main formula, and you can say that the four particles with a given charge s increases, and the velocity is decreases. When you know that when a charge particle interacts some matter, it goes inside and velocity decreases by a factor of 1 by v square, which I already told you here. Okay, and this classical expression that describes the specific energy loss, you can say that this is also known as Bethe formula. Okay, it is also known as, I can say here, it is also known as Bethe formula. It is also known as Bethe formula. I wrote here also. Okay, and what is Bethe formula? Basically, Bethe formula, I can simply write it at here. The amount of energy loss simply minus BE divided by differential path length. Okay, the amount of energy release or energy loss for a particle in a given material corresponds to the path length. Okay, it is becomes equals to, this is numerical expression, you have to know this formula, which is equals to 4 pi e4 z square divided by m naught v square. Okay, and b simply. Okay, where z square is basically, I can say that is basically the atomic number. Okay, where small z square is the atomic number, and you can say v is the velocity. V is the velocity, and or you can say, and this is the electron of the particle, electron. And where the important thing is this n is the number of, yeah, you can say number density. Okay, n is the number density, whereas you can say the capital Z, where you are written capital Z, we are written in another formula. Okay, so these are the parameters which I told you here. Okay, again, this b is equals to, I wrote here, b equals to z ln of, you can write to m naught v square divided by I minus, let me write here the complete formula, minus ln 1 minus v square over c square minus v square over c square. So this is the complete formula. When you put this b here, this becomes complete Bethe formula. Okay, and the z which I am telling is this z, and this z is basically the atomic number of the observer, atomic number of absorber material. Suppose the lead is placed in front of charged particles, so lead is the absorber material, so this is the atomic number of the observer material. Okay, and all the parameters are same. V is the velocity, m naught is the rest mass of an electron, and the important thing is this I. Okay, this I is basically ionization or excitation potential. This I, ionization or excitation potential. Okay, you can see here, I already write it right here in my notes. Okay, I will send you all the notes. Just comment me, and I will email you all the notes which you required. Okay, I have already ready made, printed in a presentation form, all the notes of all the courses. If you need any of the notes, just comment me. I will send you via me email. Just drop down your emails, and the notes which you provide within 24 hours, inshallah I will provide you. Okay, so this is the complete Bethe formula, this. Okay, so no worries if and this n and z is not given, go through your all things. Okay, so this is the stopping potential, and today we discuss about radiation interaction and stopping potential. So this is our today's our only lecture number 1. This is all about lecture number 1. We discuss there are 3 type of interactions: heavy charge particles, fast electrons, and uncharged particle. And today we discuss only heavy charge particles. In heavy charge particles, we discuss all the aspects that when a charged particle interacts with some material, what happens. Okay, with in single collision, the empirical formula is 4 E m naught divided by m. And what is stopping potential? We know that it's basically already we defined it as it's the differential energy loss of a particle within the material divided by the differential path length minus sign, because there is a decrease in energy. Okay, and we discuss about the Bethe formula. And that's all for today, and stay tuned with us. We will update you each and every lecture. This is our new series of advanced nuclear tracks, matters, principles, and their applications. So stay connected with us. Thanks for watching. Allah Hafiz.